out how to create a proof for a iterative algorithm. And so we looked at essentially, again, there's always a precondition and there's a postcondition. Just reminding me, precondition is assumption of things that must hold true before the algorithm executes. Postcondition is the guarantee of the result of the algorithm, assuming the precondition is satisfied. Okay? And so all we're trying to do here is just add up a bunch of numbers in an array. Okay? So, okay, manually. So what we have here is we're talking about an invariant condition. And the loop invariant is that condition. And basically in this case we're looking at the invariant to be the summation from a to I minus 1 of the element of j equaling the value of sum. And if you look at the initial value of the algorithm, you'll see that initially the value of I is equal to a. So before the first iteration of the algorithm, j goes from a to a minus 1. And when the upper index of the summation is less than the lower index of the summation, then there are no terms. Therefore, by default, the sum is equal to 0, which is correct, since sum is initialized to 0, and we have not examined any of the elements. Okay, then we talked about how to prove the loop invariant is actually true, and that is done by, that's the most complicated part of the proof, and that's done by induction. And again, I'm not going to ask you to do a proof by induction of a loop invariant, but I will ask you to identify a loop invariant. And a loop invariant, as I mentioned last week, was a generalization of the postcondition. So it generalizes the postcondition, somehow inserting that I value, that changing value of the iteration into the postcondition, so that it's true before the first iteration, before the second iteration, and before the iteration that never happens, which also means after the last iteration. So, since we know from the precondition, we know the precondition says that the precondition is a is less than or equal to b plus 1. So at most it's b plus 1, and at least it's something less than that. So it could be b minus 1, b minus 2, etc. Okay? So therefore, what do we know about what happens when the algorithm breaks? Well, basically the algorithm breaks when I not equal to b plus 1 is false. And when it's not, when I not equal to b plus 1 is false, that means I is in fact equal to b plus 1. So if I is equal to b plus 1, if we examine the loop invariant, if I is equal to b plus 1, then put in b plus 1 for I. So you get b plus 1 minus 1, which is b. And therefore sum should equal to the sum from a to b of all the elements, which is what we're looking for. So two conditions have to be put together. So basically, so this is just proving that the algorithm loop invariant is correct. Again, I'm not asking you to do that, but what I am asking you to do is to go through and determine what the loop invariant is by inspection. So looking at that, so now the part 3 is we want to show that the loop invariant, which is the condition we saw before, and the break condition implies the postcondition. The loop invariant has been proved, at least it's supposed to be proved, and the break condition is when the loop iteration is false. So our break condition was, our continuing condition was that I is not equal to b plus 1. Therefore the break condition is the not of that continuation condition. So when I is not equal to b plus 1 is false, that means I is equal to b plus 1. So the break condition is the negation of the continuing condition. So in this case, the break condition implies that I is b plus 1. And the loop invariant has been proved, so we want to join these two conditions. And the joining is simply substituting I equal to b plus 1, which is the break condition state, and plugging it into the loop invariant, and you can see what happens. So the break condition, along with I, implies A to B, which I just showed you a minute ago. And the last thing we have to do in an iterative algorithm is to show loop termination. How do we know the loop terminates? Well, we can argue that the I is strictly increasing by 1, and I'll go back to that. I is strictly increasing by 1, and it will reach b plus 1 as long as a is less than or equal to b plus 1 initially. How do we know it has to be equal to b, less than or equal to b plus 1 initially? Precondition. So precondition requires it. So that means that the biggest value that I would have is what initially? B plus 1. So therefore, it will break because if I is equal to b plus 1, the break condition says I is not equal to b plus 1. Break immediately. So it will break before any elements. Okay? So that means if there are no elements, the break is immediate. What if I doesn't come in at b plus 1? What if I comes in at b? Then the loop goes from a to, always starts at A, right? What are we going to go through? Up to B. Up to B. So really, so in that case, we're going to have, but there's only one element, so therefore, it's only going to be one iteration. So that means that I is going to start at A. We're going to go lower index A, upper index A, one element. B is equal to A on the upper index. So we'll do one element. And then after that, the algorithm says I++, always I++, strictly increasing. Therefore, the next value of I is going to go to B plus 1. So it's going to terminate. So that means if I starts off at B plus 1, the break is immediate. If I starts off less than B plus 1, like B, the break is after one iteration. But if the value is less than B, then it's going to be 2 or more iterations strictly increasing until it reaches the break condition. So we want to make sure the algorithm will terminate in that place. Okay, any questions about that? Okay, so that's going to terminate our discussion of the first part of the notes, and I'm going to jump into the second part of the notes, which is going to be talking about algorithm analysis. Okay, so our algorithm analysis is very, very important because now we're going to be learning sort of the mathematics behind algorithms, and that's very key for us. So in the field of computer science, the study of efficiency of algorithms is known as the analysis of algorithms. And so therefore, let's look at an example. We know that a bubble sort, yes?
Quick question.
Yes?
There was a symbol that was like a diamond.
Oh.
I just wondering what that meant.
I wonder if it was nothing. Was it on the previous notes? Was it wrong? Was it the wrong symbol or something? Was it on the previous notes or these ones? Okay, let's go back to the previous ones. Previous one should be here. Is it here?
No, previous one.
Previous slide?
Yeah, this
Oh, okay. So it was this one right here. Oh, it looks like a diamond. Okay. Yeah, so this is just less than, greater than, not equal to. Usually, you can write an exclamation point equals, that means not equal to. So it just means while I is not equal to b plus 1. So that's good that you guys picked up on that question because I didn't see the diamond. Actually, if you look, yeah, it looks like a diamond. Actually, it looks like a diamond. Because of the font. If you use a different font, it'll separate them a little bit. So I starts at A. I not equal to b plus 1 is the continuation condition. The negation of this is the break condition, which means that I is equal to b plus 1. And then joining that with the loop invariant, we then jump into the post condition, which is what we're trying to achieve as an algorithm. Is that okay? All right, so let's go to this part right here. Still dying to get this remote to work, so I can change it. It's never had this weird behavior until this semester. Okay, so we know that bubble sort, which we discussed in this class, right? We talked about bubble sort. Roughly requires about n squared statements to sort n elements. So let's say it requires n squared statements to sort n elements. And let's suppose that we can sort n elements using this number of statements in some time interval, we'll call it t. So in time t, so whatever that means so we have n elements in a bubble sort. We sort them, and they get sorted, and we stop the clock. How long did it take? T seconds, whatever that was. Well, what does it mean? It means that I was able to execute n squared instructions, approximately, in t seconds, or in time t, whatever t is. Now, if, suppose we increase the computing speed by 1 million, which is quite remarkable. If we could increase the computing speed by 1 million, then what does that mean? Well, what it means is that the number of instructions that could execute in time t goes up from n squared to 1 million times n squared. Okay? So therefore, 1 million n squared statements can be executed in time interval t. Since 1 million n squared equals 1,000 n squared, and that is the problem size, because remember, the problem size, number of instructions. Problem size, number of instructions is square of the problem size. Since 1 million n squared is 1,000 n squared, that means that in the same time t, on a computer 1 million times faster, I can solve a problem 1,000 times bigger. So somehow, 1,000, which is 10 to the third power, and 1 million, which is 10 to the sixth power, somehow, even though the speed is increased by 6 magnitudes, the problem size is only increased by 3 magnitudes. We've lost 3 magnitudes of speed up on an algorithm. So this shows, since only 1,000 n elements can be sorted, that's a square root increase, square root of the computing speed. So we lost 3 of the 6 orders of magnitude. Anybody know why? Well, it's because the number of instructions to solve the algorithm is not linearly tied to the size of the problem. It's quadratically tied to the size of the problem. The size of the problem is n, you need n squared instructions. So n to n squared. So really, to go backwards, if you have n squared instructions, you can solve a problem of size n. Okay. If you have 1 million n squared instructions, you have a problem of size 1,000 n. So because the complexity of the algorithm is higher than a linear relationship between the instructions and linear relationship between the number of instructions and its complexity. Okay, so so now let's take a look at a different algorithm. Let's say we have an algorithm. There's an algorithm that we're going to look at. It's called the swap down algorithm. It's part of a heap sort. And the number of instructions that's required is LGN, where LG is log base 2, log base 2. Okay. So for example, if I have 16 instructions, if I have the problem size 16, what's log base 2 of 16? 4. I need 4 instructions. If I have 256 is the problem size, what's log 2 to 56? 8. So okay, 2 to the 8, that's fine. Don't worry about it. So 2 to the 8. So 8. So the relationship is like that. Okay, so now let's say I increase the computing speed by 16. 16, which is not as impressive as 1 million, but still good. So therefore, in the same time as I executed my LGN statements, I can now execute 16 LGN statements. Now you may recall that 16 times log base 2 of n is equal to, we have this thing called the power rule in logarithms, which means that the factor of the log is equal to the log to the power of 16. So whatever is this factor can go up as a power of n. So that means that 16 LGN is equal to LGN to the 16th power. So therefore, since LGN is the original, excuse me, since n is the original problem size, the new problem size n to the 16th power, which is an exponential increase. So, what do we have so far? If the algorithm is quadratic, speed up the computer. We only gain square root of speed up. If the algorithm is logarithmic, we gain say it again. Exponential into the speed up. So instead of, when we speed up the computer by 16, our problem size goes up by the power of 16. Which is quite remarkable. Imagine that the original problem n is equal to 16. How many instructions do we need to solve it using our algorithm?
16.
If the original problem is 16, the number of instructions we need is log of 16, which is 4.
4.
2 to the 4th, 16. So now I'm going to speed up the computer by 16, which means I can execute the same time t, 16 LGN, which is LGN to the 16. The new problem size is 4 to the power of 16, which is, by the way, which is 4 to the power of 16 is equal to 2 to the second power, which is equivalent to 4, raised to the 16th power. 2 squared to the 16, you can multiply these exponents, and it gives you 2 to the 32nd power. Let's just put that into perspective. Originally, I could solve a problem of size. What's my original problem? What was n originally? What do we say?
16.
Did I say 16?
14.
What was my n originally? Because we can change it. I think original problem was 4. So just imagine I can solve a problem of size 4. Very, very small problem. And how many instructions are needed using this LGN complexity? 2. Now I speed up my computer by 16. Okay. Which means now I can execute 16 times LGN instructions, which is equal to LGN to the 16th power. The original n was 4. So now 4 to the 16th power is 2 squared to the 16th, which is 2 to the 32nd, which means my new problem size is equal to 2 to the 32nd. It goes from size 4. Anybody know what 2 to the 32nd is? That's 4 gigabytes. The problem size increased from 4 to 4 billion. Billion. You heard right. Why? Why do we gain so much more? So how much of the speed up do we gain? Well, it's going to be 2 to the 32nd divided by the speed up, which is equal to what? What was the speed up we're talking about? It was by a factor of 16. Divided by 16, which is 2 to the 4th. So 2 to the 32nd minus over 2 to the 4th is 32 minus 4. That's going to be 2 to the 28th power. What is 2 to the 28th power? 2 to the 28th power is equal to 2 to the 8th times 2 to the 20th. 2 to the 20th is 1,000,000, 2 to the 8th is 256. We've gained 256 million times the speed up. It's a ridiculous example, but it's a very poignant example. It shows you that if the algorithm has a very low complexity, speed up allows us to solve hugely larger problems. So, the amount of speed up that can be realized for an algorithm by using a faster machine is proportional to the inverse function of the speed up. What does that mean? Well, if the complexity of the algorithm is squared, x squared, what's the inverse of x squared? How do you turn x squared back into x? Or n squared and back into n? You take the square root. That's the inverse function. If the algorithm has a third power complexity, cubic complexity, n cubed, how do you turn n cubed back into n? You take the cube root of it. So that means the speed up you would realize is a cube root of the speed up of the machine. What is the inverse of a logarithmic function? The answer is, it is an exponential function. So log base 2, the inverse is 2 to the power. So the logarithmic function, which grows very slowly like this, is an inverse function to the exponential function, which just goes up like crazy. So the amount of speed up that can be realized using a faster machine is proportional to the inverse function of the speed up. So if the algorithm has a complexity of LGN, and the speed up is 8, then it's going to be 2 to the power of 8, 256 speed up. If the speed up is 16, 2 to the 16th power. What's 2 to the 16th power? That's 2 to the 10th times 2 to the 6th, which is 64K, 64,000. All right, so you get the idea of that. Algorithms for which the problem size can be solved are proportional to the computing speed are called linear complexity algorithms. If an algorithm has a linear complexity, like for example, n. So I have a problem of size n, and the number of instructions I need to have, 2n, 3n, 4n, is proportional to n. Those are called linear algorithms. Those algorithms realize exactly the speed up of the machine to be the increase of the problem size. It's a one-to-one. So if I have a machine that I'm solving a linear problem, and I can right now solve a million, problem size of a million in time t, and I double the speed of my machine, I'll be able to solve in time t problem size 2 million, because I can execute twice as many instructions, and the inverse function of linear is linear. For example, what's the linear function of n? How do you turn n back into n? You can multiply or divide it by 1. You get the same function. That's the inverse function. How about if the function is 2n? What's the inverse function? If you double something, how do you go back to half of that? 1/2 n, still linear. So linear takes back to linear. Quadratic, square root. Cubic, cube root. Fourth power, fourth root. Logarithmic, exponential. That's a big one. Okay. So on the next page, I just sort of have a summary of what we're talking about here. And I'll let you take a look at that, okay? I'm not going to discuss it, but I've already kind of discussed it. So this is linear algorithm, quadratic algorithm, logarithmic algorithm, and exponential. If the algorithm complexity is linear, just go down here. Problem size is n, approximate instruction size is n, speed is increased by 1 million, therefore you can do 1 million n instructions. And therefore the new problem size is going to be 1 million n. So it's one-to-one. Quadratic means that the new problem size is going to be square root of the speed up, logarithmic to exponential, and exponential to logarithmic. This is the worst one of all. If your algorithm has an exponential complexity, for example, 2 to the power of n, 2 to the power of n. And let's say I can solve a problem of size 16 in time t. So the complexity is 2 to the n power. And I can solve a problem of size 16 in time t. How many instructions are executed for that problem? Problem size is 16. Algorithm complexity is 2 to the n. 65,000, 64K, right? It's 2 to the 16, which is 64K. I double the speed of the machine. So instead of 64 instructions in time t, it will execute 2 times 64K, which is 128K. Well, how much of a problem can I solve that's bigger than 16? And it's exponential. The answer is 1 more. I get down to the 17. Because, what do I say, 16 before, 16, right?
Yeah.
So 2 to the 16th. Because what is 2 to the 17th? 2 to the 17th is 2 times 2 to the 16th. So I only added 1 to the number. So therefore, when I take the log base 2 of 2 to the 17th, I get 17. I can only increase the problem by 1 if I double the speed of the machine. If I double it again, I can increase it by 2. It's the work. It's just as bad as the logarithmic is good. Just as bad as the logarithm is good. This is incredible, except it's incredible on the bad side. So exponential logarithms are very, very bad. All right. So what we're going to look at here is we're going to look at an example of trying to figure out how we can count instructions that are being executed on an algorithm. This one specifically, we're looking at a very simple example of the bubble sort. I think we went through the bubble sort, right? All this kind of stuff in here. This bubble sort is slightly different in the sense that I go from 1 to n minus 1, from 1 to n minus 1. So therefore, that means if I go from 1 to n minus 1 and then 1 to n minus 1 again, I'm comparing this way. So that means big values are going to go down. So I'm going to check that, and I'm going to do it again, and I'm going to do it again, and I'm going to do it again. So each pass through the elements, it's the biggest element so far towards the bottom, or on the bottom. So after one pass, the biggest element is in the bottom. After 2 passes, the second biggest is also next to the bottom, etc. This is the code. Int, so I from 1 to n minus 1, j from n minus 1, if xj is greater than xj plus 1, if the element that's higher is greater than the element that's lower, then we will do this, exchange, swap. Temporary gets xj, xj gets xj plus 1, xj plus 1 gets temporary, it's a swap. Swap, swap, swap. It takes 3 things to swap. Everybody knows how to do a swap? This is how to do a swap. So we're going to swap this pen. So I want to give it to you, right? Let's see. I have 2 pens. Oh! Let's do this way. So I have 2 pens. I need to swap them. Computers are, these are both green pens, so that would be very confusing. Pens are very difficult to swap. Notice that pen has to be somewhere. I can't just say, throw them up and try to catch them. Computers are not good at throwing things up and catching them. They're just not. It's just not what they do. All right, you're going to try you over here? Okay, so just one hand I need one hand. So we're going to call this temporary. So this is xj plus 1. So xj plus 1 goes to temporary. Now, it's still here as a copy. She's got the other copy. Okay? This one goes back to the one that receives it, then temporary goes here, and so 3 operations. That's how we swap. So those are the 3 operations. So now what we want to do is we want to count them, but we want to count them generally, not for 10 elements, not for 1,000 elements, but for n elements. So the way we do it is basically we're going to go for 1 to n minus 1. So this loop, look at statement number 1. It hits, we go inside here, we come back up, and we go in again. Another loop here, we go in again. So how many times does statement 1 execute? Well, it executes from 1 to n minus 1. So therefore you think it's n minus 1 iterations on statement number 1. But actually it's n because we have to test the statement. When I finally hits n minus n, it goes up beyond n minus 1, it has to test the statement and fall out. So we call this once to be false. So n minus 1 times it's true when we go in, and 1 times it's false so we don't. So that is n total iterations for statement number 1. Statement number 2 executes every single time we go into from here to here, from outside to inside. So the first time we go in, the statement executes n times. N minus 1 plus 1 to get out. The second time, n times. The third time we go in here, n times. The fourth one we go in here, n times. So it's going to be n minus 1 times we go in, and n times we execute. So now statement number 3, we do a comparison. Well, that comparison is going to get executed every time we go into here, we're going to execute. So when the first time we go in, we execute. But how many times are we going to go in? Well, we're going to go in from here to here n minus 1 times. Not the false, but just the true times. And from here, how many times we're going to go in here? N minus 1 times. So every time we go in from here, which is n minus 1 times, we're going to do this one n minus 1 times. So that's going to be n minus 1 times n minus 1. You can see this is highlighted in yellow. The next question is, how many times do we swap? Well, that's a good question. We have no idea how often we have to swap, but we do know that we know something from our knowledge of the bubble sort, and that is, if we're going to do the swap down like this, I might be swapping every single time. But on the next iteration, I am definitely not swapping into the last position because that's already set. So it's going to be not n minus 1 swaps, but n minus 2. On the next one, the maximum number of swaps is going to be n minus 3, n minus 2, n minus 3, n minus 4, n minus 5, all the way down to until we only have one comparison where the maximum number of swaps is going to be 1. Since the maximum number of swaps on the first pass is n minus 1, and then it's decreasing n minus 2, n minus 3, n minus 4 down to 1, that means if we do a summation from 1 to n minus 1, summation from 1 to n minus 1, meaning 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus n minus 1, if we do that summation, that actually is equal to n minus 1 times n over 2. And I'll show you exactly how it's done later on. If you don't remember, don't worry. But basically, so therefore, I'm going to say n. So I have n times n minus 1 over 2. Now, this is the number of executions. So now, I'm going to give it a more precise number, because this one is a little quirky, but basically, really what we should do is we shouldn't just do this, and do this again, and do this again, and do this again. We should really go all the way down to minus 1, minus 2, minus 3, minus 4. All of a sudden, by the time we get here, it's only one comparison. So we're overkilling it here. So what I tried to do is I tried to average these statements together, put these statements into here. So what we need to do is the number of executions, all we need to do is add up this, and this, and this, and this. And when you get that, you simplify it, and you come out with this box right here. And this box right here is what we call, we can call it an instruction count. Instruction count, we're truly counting instructions in the algorithm. So in this case, we have 7n squared, 7 halves n squared, minus 13n over 2, plus 5 over 2. Now notice that this is truly a quadratic function, because n squared is the highest order polynomial term. When n is a million, this is 3.5 trillion, and this is 7.5 million. When n is 1,000, this is 3.5 million, and this is 7.5 thousand. So you can see as n is increasing, the n term is getting blown away in magnitude by the n squared term, and of course the constant is just 2.5. So when we're talking about large n values, the constant disappears very quickly, but the linear term disappears a little more slowly, but as n is increasing, it goes essentially effectively to being a non-factor. So therefore, really we concentrate on 7 halves n squared.